Well, hello, and congratulations. You've made it through another chapter. And frankly, I like math. I majored in math. And I found this last chapter to be fairly boring. I expect you did too. Well, they can't all be winners. You gotta expect that once in a while. So, let's review and remember. Transformations, similarity, especially symmetry, for instance. It's all kind of boring, but it's going to be on the standardized exam. Plus, it's not too complicated. Notice there aren't a whole lot of equations involving transformations or symmetry. A few theorems, but not much. So overall, it's just some facts you need to memorize, which in my opinion is antithetical to mathematics, but state exams, they are what they are. And if you need to memorize some things to do well, then what the heck. Your brain won't get worn out by memorizing, so I wouldn't sweat it too much. What do we have here? I want to see all the lines of symmetry in this window design. Now, it's tempting to look at this as a, gee whiz, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8, a 16-agon. Well, it's tempting to look at it that way, but it won't quite work because of all these extensions that go beyond the actual polygon here. So the symmetry of this turns out to be exactly the same symmetry of a rectangle or a square. We can draw lines along the diagonals, and if we were to fold this over, it would fit perfectly. In other words, everything above this yellow line is identical to what's below it, and that's true for each of these lines of symmetry. As I say, it has the same lines of symmetry that a rectangle or a square would have. What about rotational? Well, again, this one's more like a square, not a rectangle. So a rectangle would not have 90-degree symmetry, but this does. Of course, it also has 180. If it's 90-degree symmetry, then it kind of goes without saying, I think, that it would be 180. That's just 90 degrees twice. And remember, they also called that point symmetry. I don't know if you'll need to know that on the state exam or not, but what the heck, you might as well know it. Well, that was pretty easy. We drew in our lines of symmetry. The rotation is 90, and if you want to be totally complete, you could say 180 also. Although, like I say, it seems to me that integer multiples of the rotational symmetry would also produce symmetry, or a symmetric transformation, you could say. We could rotate it 90 degrees, rotate it 180. We only talk about 0 to 180. You could rotate it 3 times 90, which is 270, and that would work too. Now, this question at the end, they ask us to include a graph. Now, these are sample questions from standardized state exams. I'm not sure they would give you graph paper along with these or not. So I'm not going to use one of my preset graphs. When I graph it, I'll probably just draw a couple of quick axes, mark off some tick marks on them, and do it the way you would have to do it on the exam. At least I think that's what you would have to do. If they gave you graph paper, then that's even easier. What they have is, or what they want, is the image after successive transformations. First one's a dilation. In the absence of any other information, we're going to have to assume that this is a dilation about the origin, the point 0, 0. It doesn't say anything else, so we can't assume anything else. Translation would be next. Now, we can do this fairly easily. By easily, I mean algebraically. Start with A, for instance. 0, 2. Well, A prime would be 0, 6. And A double prime. Now we apply this transformation, subtract 2 from each of them, and get minus 2 and 4. Now we can do the rest of the points the same way. Start with 2, 0. Under our dilation with k equal to 3. That's basically what this says here, right here. That's the same as... Oops. Well, I didn't notice, but this is a misprint. 3x comma 3x. That would definitely not be a proper dilation. That would skew things terribly. Your y-coordinate would become your x-coordinate, and really wouldn't make any sense. For instance, if we did it this way, instead of 0, 6, we'd get 0, 0. And that's not going to be the right answer. If you try it this way, you take your 0, 0 here, and then do your transformation here, and you will end up with something that is not congruent and not similar, like you're supposed to get with the dilation. So this is really supposed to be 3x comma 3y. That happens, and I've seen misprints in practically every math book I have used, at least when I was teaching. As a student, I probably found misprints, but they drove me crazy because I didn't know enough about the material to know for sure that they were a misprint. So I wasted a whole day trying to work the problem with the misprint and finally gave up. But as you, luckily with experience, you start to notice misprints and figure out that this could not possibly be what they meant. This is, what I mean is this one here, forget this part. 3x, 3y is the same as 3 times xy. I mean, this is your k right here. So, once you've written it correctly, we transform 2, 0 into 6, 0, which becomes 4 minus 2 under the translation, minus 2 minus 2. This is the vector here that we would just add to whatever we get here. Same thing here, and we end up with minus 8 minus 2. Now for the freehand graph. This will be good for a laugh. These are the points that they asked us to plot. Here's x and here's y, more or less. If you're wondering, I do this a little better on paper, on chalkboards, grease boards, and I'm using a small graphics tablet. Kind of set up like an easel. The friction is different or something, I don't know. Maybe it's just a dumb excuse. Maybe there's no good reason for it. I'm just not very good at using these things. So let's see, here we go. 1, 2, 3, 4, 5, 6, 7, and 8. Our final answer is minus 2, 4. Oops, 4 is up there. 4 minus 2. And minus 8. 2, 3, 4, 5, 6, 7, 8. Minus 2. Down here. If we were to graph our original figure, maybe I should use a different color so it should. That would be 0, 2. Pardon me. 0, 2 is this one up here. This is 2, 0 over here, and minus 2, 0. Well, I think you can see that this figure is similar to this one. Maybe you can't because the drawing is so darn bad, but might be able to see that if this drawing was correct and this was correct, these two lines would be parallel, and this side would be parallel with this, and this side would be parallel with this one. In other words, we haven't changed any of the angles. We just enlarged everything by a factor of 3. And of course we shifted it also off to the left and down. And this is to the left and down. You can see how that worked out. Pardon me. And like I said, for fun, if you'd like to, you can try doing it the misprint way, 3x and 3x, and see what you get. And you will definitely not get a figure similar to this original blue triangle. The way this problem is worded confused me for a second, and I think what they mean is there is a transformation which takes the blue square into the red square. In other words, this lower one is the image of this upper one here. And what they're asking is, what could that transformation be? Or describe 3 different transformations which could be that single transformation that sends the blue square into the red square, or causes the red square to be the image of the blue square. In other words, they don't need a succession of 3 transformations which produces this image. And they say that it's a single transformation that does it. Well, the 3 that you're describing, one of those would be the one that is the single transformation that does this. And it could be any one of 3. So what are those 3? Well, first off, I'd say it seems kind of obvious that this part is a reflection of that. So if you reflected about the line, call it a reflection about y equals minus x. That's that line right there. How do I know that? Well, that's the 45-degree angle. Remember, that's y equals x is that one, and the one goes the other way, it's perpendicular, that's y equals minus x. Those are 2 that are, well, y equals x is super easy, y equals minus x is almost as easy. Only a hair's difference in how easy they are to remember. That's one of them, the reflection. Number 1. What about rotations? Well, if we rotated this 180 degrees, wouldn't that put this corner right here? And this one would go right there, this would come down to here. Remember, this 180 degree rotation is just like flipping this line over to here. And that's exactly what this is. We just take this, if this square were connected to this line, like they were, this is plywood and this was a board it was nailed to, if you flip this board 180 degrees, you would end up with exactly this configuration. So, the second one is a rotation of 180 degrees. What else? Well, let's see, we have reflections, rotations, and this is a congruence transformation. What's our other congruent transformation? Reflections, rotations, translations. So, what if we just shifted this along the line x equals y, but down? Yeah, it's kind of a dumb way to put it. How about we shift it along this vector, which drops y by the length or the side of the square. For instance, if we call S the side of the square, and the same for all of them, of course, then we could transform it by saying that xy, this is a translation now, goes to x minus S and y minus S. That'll drop it down here and off to the left. Drop it down the length of a side, off to the left the length of one side, and that'll put it right there. So the reflection about y equals minus x, 180 degree rotation, or number 3 is translation by the vector, or if you like the standard vector notation. Well, that's supposed to be an S, not a 2. Jeepers. Minus S, or minus S times 1, 1. Either one's okay. This is probably more, this is only one vector. This involves a multiplication. So if you were going to put it here, it would probably be more standard to write it like this. Well, here's one which we'll have to think back a little bit to our section on quadrilaterals. What the heck does this have to do with transformations? They're asking us to find the measures of the 4 interior angles of this trapezoid. And in fact, it's an isosceles trapezoid, which helps a lot. We know that these 2 base angles are congruent. We also know that these 2 angles are congruent because it's an isosceles trapezoid. But that allows us to set up an equation, something like if we call these 2 angles x, we only have to have one variable because they're congruent. Same for these 2. And the interior angles of a quadrilateral, they add up to 360, right? So we could write 2x plus 2y equals 360. But the problem is, we've got 2 variables, 1 equation. That's not going to work out too well. That just gives us a line. Remember, we could write this x, we could write y as a function of x. That would give us a line we could graph. That's not going to tell us what the heck these angles actually are. But these are all the same trapezoid, and there are 6 of them, which means this thing has rotational symmetry. The fact that there are 6 of them is not what gives it rotational symmetry. The fact that each of these is congruent, we can rotate one into the next one, and there will be no difference. That's why it has rotational symmetry. But how many degrees? Well, there are 6 of these congruent trapezoids that we can map onto each other by rotating. And that means it has 60 degree rotational symmetry. That means that if I take this line and rotate it 60 degrees, it becomes this line. Well, this line here is really the base of this trapezoid. It's the base of this trapezoid. It also forms a side of this isosceles trapezoid, which means that if I rotate this side onto this side, I've rotated 60 degrees. That's the angle between this side and this side on this trapezoid. So I just write it in here, 60 degrees. Well, that means this one is 60 because they're congruent. 60 and 60 is 120. And the interior angles add up to 360, so I've accounted for 120 of them. If I subtract 120, I get 240. Now, if I divide that by 2, I've got 240 degrees left over, which I have to distribute across 2 equal angles. So I divide it by 2 and I get 120, which means that each of these is 120 for both. Where transformations came into this was recognizing that this had 60 degree rotational symmetry from this equation here, and this turned out to be unused. All we needed was our rotational symmetry. That gives us this angle, and then we can work out the rest from what we know about isosceles trapezoids. Okay, here's a good problem, because it shows that, let's see, I probably got to use my line tool. If I try to draw the line, it's going to be so bad. Hold on. What this problem is going to illustrate is that if we take this crooked path to point D, and we're going to write out this vector, and then the vector that takes us from B to C, and then the vector that takes us from C to D, and we're going to find that when we add up these three vectors, we're going to get this large vector once we figure out what this large vector is, which is going to be pretty easy. So, let's start. I think they wanted us to write down, yeah, A, B, B, C, and C, D. So, it's going to be A, B is what? Well, we went from 0, 0 to 9, 6, so when a vector starts at the origin, it's very easy to write down its components. Just 9, 6. So, first we list the vectors which represent our displacements. From 0, 0 to point B, that's a displacement of 9, 6. 9 units to the right and 6 units up. Here, 17, 0. Well, from the point 0, 0, that's a displacement of 17, 0. But we didn't start here, did we? The vector we want is the one from B to C, which took us from 9, 6 to 17, 0. That means we went up 8 to the right 8. We increased the x-coordinate 8 units to right here. The y-coordinate went down by 6 units. Well, there's our minus 6. So that's our vector that takes us from here to here. We can even write it in. What the heck? 8 minus 6. That's this vector. And this one here, well, our x-coordinate increased, went to the right from 17 to the 24. Well, that's an increase of 7 units. And it went up from 0 to 16, which is obviously an increase of 16 units. And that makes this our new vector, or our displacement, really the same thing, is 7, 16. So we have the vector 9, 6, the vector 8, minus 6, and then the vector 7, 16, and we wind up here. Well, we already know, because this starts at the origin, AD is just 24, 16, the same as the point. That's how it works when you start at the origin. If you're not at the origin, you have to subtract and get the displacement. If you're at the origin, well, you can still subtract 0, 0 if you want to, but you're just going to end up writing down the coordinates of the point. How does that compare to these three? Well, remember how to add vectors? If we have two vectors, AB plus CD, A plus C, comma, B plus D. In other words, you just add them up component-wise. You add up your two x components, you add up your y components. And of course you can extend this to as many vectors as you want to add. In this case, we've got 3 of them. And I'm just going to stack them, make it easy. We've got 9, 6 here. We've got 8 minus 6. And we've got 7, 16. If we add these, what do we get? 8 and 7 is 15, and 9 is 24. 6 minus 6 is 0, plus 16 is, of course, 16. And what were we to be? 24, 16, 24, 16. In other words, it doesn't matter how you arrive at this point. The vector is going to be the same. we could have taken 23 different odd vectors zigzagging all the way up to the point 24, 16, and when we added up all 23 of those vectors, we would get our vector 24, 16. It's kind of it's a graphic way of adding. We've added all these up, and we've wound up at the endpoint. We're adding them graphically by adding. We take 9, 6, we add the vector 8, 6. In other words, we go 8 to the right and 6 down. That puts us over here. And then we follow this vector here, the 17, 7, 16 up to here. And wherever we end up, that is the actual sum of all the vectors that got us here. And the same thing would be true for differences. For instance, this vector minus this vector here, the 7, 16, would put us here, right? And in fact, if you do this, 24, 16, subtract 7, 16, you're going to end up with 17, 0. So you could take your vector 24, 16, subtract this vector, and that puts you right here, which is exactly what would happen if you just added these two and didn't add this one in. Again, it's a graphic form of addition. Wherever your vectors end up, that would be the sum of all those vectors. Well, here they're telling us to reflect a polygon in the x-axis. A triangle's a polygon, so that's probably as good a one to use as any. And then reflect it on the y-axis. Now that would be the equivalent of a rotation. The question is, what rotation? And they ask you to draw an example. So I drew in an xy the way you would have to do it on a state exam. As I said, if they give you graph paper, great. Otherwise you'll have to freehand, I think. Maybe they'll let you use rulers too. Probably depends on the school. Here we have a reflection about the x-axis. We'll start with this, and what would our reflection be? Well, this point ends up here, this point ends up here, and this point right here. There's our reflection about the x-axis. Now we have to reflect it about the y-axis. And this point looks like it'd go right about there. This point right there, and this point would end up right about there. Well, this looks like we went from quadrant 1 to quadrant 3. What's that? That's a 180-degree rotation, isn't it? For instance, if I'd drawn this better, I'm surprised this isn't all that bad. We have this straight line where this side rotated right into this side here. Well, that straight line is 180 degrees, right? So these two reflections would be the same as a 180-degree rotation. About the origin, of course. Well, here's a problem where we've got a couple of rectangles. One is the image of the other under a dilation with a scale factor of 1/2. And they tell us the area of the image. That's this one. This one, A prime, equals 32 square inches. Or inches squared. They want us to find the lengths of the original. That would be the pre-image. Well, if we knew the area of this, we could do it, because we'd have 2x squared. X times 2x is the original area. So we can go ahead and write that down. X times 2x, which equals 2x squared. And that is the area, We don't know what that is yet. We just know it's the area. This one here, okay. This is a reduced everything by 1/2, right? So that means the length of this is x. And this would be x over 2, wouldn't it? Because they gave us the scale factor right here. So reduce everything by the same amount. And the funny thing is, we could answer this question right off the bat. Because we've done it before. We already figured out that the areas go back and forth as the square of the scale factor. So we could immediately write 1/2 squared or 1/4 as the ratio. But let's do it this way and see what they're getting at. They're maybe demonstrating something else. We'll see. This is 32 square inches, and what we have here is x over 2 times x, which is x squared over 2. Which makes sense, because that's exactly 1/4 of 2x squared, isn't it? So we're definitely on the right track. Let's try it over here. We got x squared over 2 equals 32. Or x squared equals 16, which means x equals 4. Right? 4 squared is 16. Well, if x is 4, that means this is 4. And this is 8. It's 4 by 8. And the ratio, of course, well, I should just delete this, but it's instructive to see what happens when you do things in your head like a dope. This is wrong. This is wrong. It's not 4 and 8. Gee whiz. I divided each side by 2, which would make sense if I had 2x squared like I do over here. But I don't. I have x squared over 2. I need to multiply each side by 2 and get that x squared equals 64. And that leads to x equals 8. So this side here is actually 8. So if we actually work out the equation correctly, we get 8 by 16. So what's the area of this? So once we have the correct dimensions, what do we have here? 8 times 16 is 128. And if you multiply 32 by 4, you will get 128. And that means the ratio is 1/4, just like I said, and we already figured out that if k is 1/2, then the area is going to be k squared of the original, or 1/4 of the original. That's always true. In other words, I think I've written this before, but you could write it such that a prime, your transformed area, always equals k squared times a. That's because of the extra dimensions. It's obvious with this. With triangles, it's not as obvious, but it's still true. The area will always change as the square of the scale factor. And now, as long as it's here, I'm going to do something kind of like what the old Greeks would have done. We say that this area is 1/4 of the original, because our scale factor is 1/2. Suppose we try it. We put our transformed rectangle right there. Now let's make a copy. And put it on there. Whoa. Kind of looks like a fit. If we copy that, we'll put it, lay it right on top. Well, what do we have here? It looks to me like, well, I could actually put the last one on there. The lines actually, the crossed lines created by the first 3 rectangles that I dropped on top kind of produced a 4th rectangle, but I could actually slide it up on top as if we were working with the actual physical rectangles, pieces of wood or something. And there we go. We took one that was constructed to the dimensions given, and if we do that 4 times, those 4 rectangles will fit right into our original rectangle. And that's what's supposed to happen. Well, there's a pretty easy one. If you remember what isometry means, then we don't know which transformation is not an isometry. Remember, iso means equal, metria, measure, equal measure. An isometry is the same as a congruence transformation, also called a rigid motion or rigid transformation. And by now I think we know that translations don't change the size of the object. Rotation, that won't change the size of the object either. Reflection, same thing. These are all isometries or congruent transformations. This one, no. That's not an isometry, unless the scale factor happens to equal 1. But that's kind of a pathological dilation, you could say. It's not a very... It doesn't really qualify as a dilation. Normally when k equals 1, you call it something else. In fact, it's almost nothing if k equals 1 because you don't do anything. It's the same as multiplying something by 1, which of course has no effect. So D, dilation, is the one that's not an isometry. Now this one, they're talking about lines and slopes. You'd think you'd need to graph something, or at least draw some lines. In reality, we don't really need to. Remember, what's the slope? The change in the rise over the change in run, or delta y over delta x. And when we have coordinates for points, computing the new coordinates for a reflection about the x-axis is super easy. We just have to change the sign of the y-coordinate. We flip it. If the y-coordinate was negative, it would be positive. Remember? We're going to rotate it about this axis here. Well, if we're up here where y equals 2, then we're going to be down here where y equals minus 2. We just changed the y-coordinate. That's the second coordinate. I don't know what the first coordinate would be. So I guess what I'm getting at is, for a reflection across the x-axis, we have a transformation that looks like this. You probably remember that from the previous section where we discussed them. So, our j prime is 2 minus 5. And doing it in my head, I'll probably make a mistake, but I hope I can at least negate something in my head without making a mistake. We'll see. K prime is minus 4 and minus 13. Now, what's the new slope? Well, what's delta y? Minus 5 minus a minus 13 all over 2 minus a minus 4. Well, that's the same as minus 5 plus 13, and I think that's 8. Two minus a minus 4 is 6. So we get 4/3 for our new slope. So for this, all you got to do is remember how to compute the new coordinates when you reflect something about the x-axis, and then remember what the slope is. If you remember both of those things, this problem was really easy. Well, this problem looks like it's more complicated than it really is. I'm talking about rotation, a rotational transformation about the point P. Now, it's tempting to think that you suddenly need to figure out what the rotation was. No. All you need to do, the only way this problem actually applies to transformations, is recognizing that a rotation is an isometry. It doesn't change any of the dimensions. So, all we have to figure out is the corresponding sides, and we can start working things out. For instance, here's our right angle, and here's our right angle. Looks to me like 4y plus 2 has been rotated into x. So we could write 4 plus 2 equals x. Now here's an hypotenuse for sure. It goes into the hypotenuse. So we could write 2x minus 1 equals 5. We get 2x equals 6, or x equals 3. If we put that in here, then we get 4y plus 2 equals 3. And, yeah. I need to redraw. I want to put it right here because it looks like it goes with this, and it doesn't. This follows from this. This part follows from this after we have that x equals 3, so I can write this and rewrite this as 4y subtract 2 from each side equals 1. And so we would end up with y equals 1/4. I think that's what they asked us for, to find the value of y. So aside from, remember we just had to match up corresponding parts. This part corresponds to this. The hypotenuse, of course, corresponds to the hypotenuse. Remember that the rotation is an isometry, which allows us to say that after the transformation, corresponding parts are still congruent, still equal. That's why we can set this up and end up with this. Again, pretty easy if you just remember the facts about rotations and corresponding parts being equal. Well, here's one that's tempting to work just like some of the others we did, but that's kind of what we're going to do, except they only asked for the x-coordinate of q prime. Now we transform these points one at a time, and then we connect them up to get our new polygon. Well, they're not asking us for the new polygon. They're not asking us to graph anything. So why do we even care what P and R, what R and P are? Boy, I don't like the way that sentence sounds, but I guess I'm stuck with it now. Let's just take a look at Q. First we have a translation. Q under what? Minus 2, 1. That's the vector of the vector motion. We could say that this translation amounts to. Well, Q was what? 2, 0. So it's going to go to 0, 1. Dilation centered at 0, 0 with k equal to 2. We just have to multiply everything by 2 and get 0, 2. They only asked us for the x-coordinate of Q. Is it? Yeah, x-coordinate, and that of course is 0. So in fact I did twice as much work as necessary. I could have just added minus 2 to 2 and gotten 0, multiplied 0 by 2, and still gotten 0. Didn't even need the y-coordinate. I think this is one of those trick questions, where if you didn't really think about what you were doing or felt that you had to draw pictures, you'd waste tons of time graphing all this, performing 2 different translations on the entire polygon to arrive at this simple little answer when all you really had to do was this. Here's one that looks a little tricky, but it's actually fairly simple. Just take it one step at a time here. I guess I can see if I can sort of draw an XY axis. Okay, that's sort of an XY axis. Now the line 3x would go through the origin, and that's a slope of 1 where y equals x, right? So it's going to be a little higher than that. Let's pretend that's our line. Well, if we were to plot the points of this line, they would all look like this. X, 3x. X is 0, y is 0. When x is 1, y is 3. Just like it says here. And that's what this gives you, x, 3x. Okay, I only did this because we're going to reflect this. And remember how we reflect things? It's xy. We're reflecting about the x-axis now, which means we simply negate y, and we go to x minus y. Well, if every point on this line can be written as x, 3x, then every point on the reflection could be written as x minus 3x. That'll bring this point comes here, this point a little bit farther, this point goes way up here, because the negative of negative is positive, and we end up with, oops, it's supposed to go, gee whiz, it's supposed to go through the origin. And then on down this way. Whew, boy. That's the line. This line reflected becomes this line. Well, what's the equation of this line? How about y equals minus 3x? That's what they asked for here. Well, make a conjecture about the equation of the image of that line when it's reflected, and I think I just did that. I just showed you that if you write it this way, right, x, and then whatever y is under this equation, in this case it's 3x, produce the reflection, which means y becomes minus 3x, or y equals minus 3x, and it's actually always going to be y equals minus ax. They want examples. I don't really understand why. Let's suppose a equals the square root of 85. Well, then we have one case, y equals the square root of 85 times x, or, and the reflection is y equals negative square root of 85 times x. If I put any thing in, I don't know why they wanted 2 examples or 3 examples. I mean, just a is any number. Make up any number, put it in front of x, and then write down the negative of that number, put that in front of x, and you've got the 2 equations. Not sure what what they were trying to get across here, but I think a is useful enough. It tells you that when you reflect it about the x-axis, you just change the sign of the y-coordinate. I mean, I could have written this as change the y equals 3x to minus y equals 3x. That would still give us y equals minus 3x, right? We just multiply each side by minus 1. So you can come up with 15,000 examples if you'd like to. or you can just stick with, I would just stick with A. A is any old number, and whatever the number is in front of the x, that's the slope, and the slope just becomes negative. Everything else is the same. I think I already showed you something exactly like this. I'm not sure it was part of a problem, but I was demonstrating that successive dilations can be treated as just one dilation with a scale factor that is the product of the two dilations. That's what this problem is intended to demonstrate. But of course, since you've been watching my videos, you already know this. Well, let's see. First we have to find the coordinates of the vertices of our image after a dilation with a scale factor of 2, and the dilation is centered at the origin, which makes everything much easier. So f prime is going to be 8, 4, because when the dilation is centered at the origin, all we have to do is just multiply our coordinates by 2, piece by piece. Multiply x coordinate by 2 and the y coordinate by 2. This one, minus 4, and oops, that was E. Oh, I see. Well, I can correct that mistake pretty easy. Okay, E is 8, 4. F, that is E prime, of course. F prime is minus 4, 2, just double both coordinates, and G prime is 0. 2 times 0 is still 0. Minus 6. Now, what we'd like to find is our next set of coordinates under another dilation, centered about the same point, the origin, with a scale factor of 2.5. Now that's, again, fairly easy, because it's centered at the origin. E double prime, 2.5 times 8 is 16 plus 4 is 20. And that's 8 plus 2 is 10. F prime, or pardon me, F double prime now. That's minus 10. 4 plus 1 is 5. And then we have one more. 2.5 times 0 is 0. 2.5 times 6 is 12 plus 3 minus 15. So there's our coordinates after our second dilation. And what does that mean? Well, I bet if I take my first coordinates and multiply them by, let's say, oh, here we go. They're going to call our scale factors A and B. I don't like that. Let's try K1 and K2. Well, if we wanted to go directly from EFG to the double image, E double prime, F double prime, G double prime, or maybe I could just write EFG double prime, we can just use one scale factor, which is equal to the product of these two. That's what I would claim. In fact, I've said it before. Let's prove it, or at least see if it's true in this case. Suppose I multiply 4, what would be the product of 2 and 2.5? That's K1 times K2. 2 times 2.5. And I think that's 5, right? Suppose we just used one transformation, which was a dilation, with a scale factor of 5 centered at the origin, where would I end up? Well, E4 would go to 20, pardon me, E would go to 2010. 2010. Okay, we're on the right track here, I think. Minus 2, 1. Well, minus 2 times 5 is minus 10. 5 times 1 is 5. Minus 10, 5. Looking good so far. And here, 5 times 0 is 0. 5 times minus 3 is minus 15. And what do we have here? 0, minus 15. So, no big surprise. We can compose dilations, and our resultant transformation is the same as one dilation with a scale factor equal to the products. So we can do this as many times as we want. We can apply 53 dilations, and that is the same as applying one dilation where K equals K1 times K2 times K3. No, I'm not going to write out all 53 Ks. Dot, dot, dot usually stands for all the rest of the stuff in the sequence, all the way up to K sub 53. Or, to be even more general, K sub n. You could have 500,896 dilations. Simply multiply your 5,986 scale factors together, and that will be the scale factor you would use if you just wanted to perform one dilation that accomplished the same thing. They said graph it. Well, I'm going to let you graph it because you know how to do that by now. Start with these points, then graph these. Well, start with these points and then connect them so you got your triangle. And then these points, and then these points. And when you do that, it will be easy to see. Just as it's easy to see algebraically, you'll also be able to see graphically that the two dilations are really the same as the one dilation with a scale factor equal to the product of the two scale factors. Well, the next chapter is on circles. I'll see you then.